You know, it used to be that when you made a phone call, you could literally trace the physical path of your voice.
Oh, yeah, totally. Just a literal physical wire.
Right. You had this heavy rotary phone on your desk, and from that phone ran a single copper wire. And that wire went out to the street, connected to a local switchboard, and eventually reached the exact person you were calling.
It was a very linear, very physical utility.
Exactly. I mean, a single company owned the phone, the wire, the switches, the whole experience. It was something you could see, you could touch it, and you could actually understand how it worked.
It was incredibly tangible. You had this physical, dedicated circuit that opened up exclusively for your voice. And it just stayed open, tying up those physical resources until you hung up the receiver.
The logic was strictly mechanical. But today, for you, the listener, the reality could not be more different. I mean, you pull a smartphone out of your pocket, you stream a live 4K video while walking out of a building, and you leave a Wi-Fi network and just instantly connect to a 5G network.
Without even a glitch in the video.
Right, without dropping a single frame. The sheer amount of invisible architecture required to make that seamless transition happen is just staggering. And that is our mission today. We are decoding that invisible infrastructure.
It's a huge topic.
It really is. So welcome to the Deep Dive, where we always love unpacking how the world actually works with you. Today, we are diving into Ron Legarski's book, The Complete Guide to Modern Telecommunications Solutions.
A fantastic resource, really.
Yeah, and specifically, we're going to focus on this critical framework he outlines, which is called the functional layers of the connectivity stack.
And that word, stack, is really vital here because telecommunications has morphed from that single copper wire into this hyper-complex, multi-layered ecosystem.
It's not just one thing anymore.
No, not at all. The physical hardware, the operating software, and the services you actually use have been totally decoupled from one another. Legarski breaks this down layer by layer, showing how they basically stack on top of each other to create our modern digital nervous system.
And I'll just say this up front. By the time we finish walking through these layers today, you will never look at your smartphone's connection the same way again. So let's unpack this, starting right at the surface.
The part you actually physically interact with every day.
Exactly. Legarski calls this the access layer, or the digital entry point.
Right, and historically, the telecom industry called this the last mile. Representing that final stretch of wire running from a local hub to a residential home.
But he notes that terminology is kind of fading, right?
It is, yeah, because the modern access layer is entirely heterogeneous now. It is definitely no longer just a twisted pair of copper wires.
It's a mix of everything.
Exactly. It encompasses this enormous variety of technologies that all operate simultaneously. So you have fiber to the home, which provides massive bandwidth to stationary routers. You have 5G cellular networks blanketing urban centers with high-frequency radio waves.
And it extends way beyond the ground now, too. I mean, we are talking about low Earth orbit satellite constellations like Starlink beaming broadband down from literally space.
Yeah, alongside incredibly dense Wi-Fi 6 and 6E networks operating inside stadiums and corporate offices.
So all these different mediums, the glass fibers, the terrestrial radio waves, the space-based signals, they all make up the access layer. But the most fascinating concept Legarski introduces here isn't just the variety of connections.
No, it's the trend of convergence.
Yes. True convergence. Explain how he defines that, because it kind of blew my mind.
Well, true convergence is essentially the holy grail of modern networking. It means the end-user device, so your phone, your laptop, maybe an autonomous vehicle, it can move across all these different physical mediums without the user or the app they're running ever noticing a change.
So to really visualize the mechanics of this, I was thinking it's like a highly fluent bilingual person who is constantly switching between Spanish and English mid-sentence, just depending on who walks into the room.
That's a great way to think about it.
Yeah, because the speaker, which represents the smartphone's software, holds both languages in their head simultaneously. They don't have to stop talking, consult a dictionary, and restart the whole conversation just to switch languages.
Right. The transition is fluid.
Exactly. The device's internal software is constantly scanning the environment, evaluating the latency and signal strength of, say, the Wi-Fi protocol versus the 5G protocol, and it makes a real-time decision to route the data packets through whichever medium is most efficient at that exact millisecond. Like an Olympic relay race where the baton is passed so smoothly the runner doesn't even have to look back.
That bilingual analogy perfectly captures the shift in intelligence, actually. Because in the past, the network logic was tied directly to the physical circuit.
Right.
If you paid for a specific provider's connection, your device was essentially a dumb terminal. It was completely relying on their physical routing logic.
But wait, so does this convergence mean the old idea of being tied to a single provider network is basically dead at the device level?
At the device level, yes, absolutely. Today, the intelligence has shifted to the device itself and the cloud. Because the device can just evaluate the environment and grab whatever connection is best, the access layer is increasingly viewed as just a raw commodity.
It's just bandwidth.
Exactly, it's just bandwidth. The concept of being locked into a single provider's walled garden at that entry point is totally dissolving.
Wow. Okay, so the access layer is essentially the skin of the network. It's how your data permeates the boundary and actually enters the system.
Yep, the entry point.
But once your data successfully enters through that seamless skin, it still has a really long way to go. I mean, it has to cross a city or a country or even an ocean in a matter of milliseconds just to fetch that 4K video stream.
Or to send your voice to a colleague on a call, yeah.
Right. So moving from the skin, we enter the arteries of the system.
And those arteries constitute the transport and backhaul layer. This is what happens once you move past that local cell tower or your home Wi-Fi router.
You enter the domain of high-capacity optical transport networks.
Exactly. This is where fiber optics totally rule. But to really understand how we move the sheer volume of data that modern society generates, we have to look at the physics of modern fiber. Specifically, a technology called dense wavelength division multiplexing.
Or DWDM. And Legarski's breakdown of DWDM is honestly mind-bending.
It really is.
Because in the early days of fiber optics, you took a strand of pure glass, which is roughly the thickness of a human hair, and you pulsed a single laser down that tube. Light on meant a 1, light off meant a 0.
Right. It was fast, but it was just a single lane of traffic.
Right. And DWDM fundamentally alters that limitation. It applies the principles of a prism.
Yeah, so instead of firing one single laser, DWDM equipment takes dozens, sometimes over 100 different colors or wavelengths of light, and it shoots them all down that exact same microscopic strand of glass simultaneously.
Which is crazy to think about. And because different colors of light operate at different frequencies, the photons literally don't interfere with each other.
Exactly. They share the same physical space without colliding.
So you take a 1-lane road and instantly transform it into a 100-lane superhighway. And you do that without having to dig up the ground to lay a single new cable.
And that multiplication of capacity is exactly how a single undersea cable can move tens of terabits of data per second between continents. The entire architectural strategy of this transport layer is built on massive over-provisioning.
Over-provisioning meaning just building way more capacity than you need.
Yes. The goal is to build physical pipes so unbelievably large that sheer capacity prevents traffic jams. Legarski notes this layer is increasingly packet optical, which basically means it's blending the logic of data routing with the raw, pure speed of shooting photons through glass.
Okay, but let me push back on this whole strategy of infinite capacity for a second.
Sure.
If we have this massive over-provisioning and we have DWDM multiplexers acting as giant, limitless systemic arteries firing photons at the speed of light, why do we still experience lag?
The lag question.
Yeah. I mean, if I'm on a video call and the video suddenly freezes or my voice sounds like a stuttering robot, where is that delay coming from if the arteries are that wide and that fast?
That is a great question, and it gets to the fundamental limitation of standard IP routing. So the speed of light is a constant, right? And moving data from New York to London through a fiber optic straightaway is virtually instantaneous.
Right.
But data on the internet does not travel in one continuous unbroken stream. It travels in discrete chopped up chunks called packets. The straightaways on our optical highway are incredibly fast, but the intersections, which are the network routers, that is where the system bogs down.
Because the riders have to act as traffic cops for billions of microscopic vehicles.
Exactly. Think about the mechanical process of routing a packet. In traditional networking, every single time a data packet reaches a physical router, that router has to physically catch the packet into its memory.
Okay.
It then opens up the packet's digital header, reads the destination IP address, and consults this massive internal database called a writing table to figure out the most efficient next step.
That sounds like a lot of work for one little packet.
It is. It makes a decision, puts the packet in a queue, and finally sends it on its way. This is known as a hop-by-hop methodology. And doing that millions of times a second requires intense computation processing power, which inherently just takes time.
Right, and if a router gets overwhelmed, those packets just sit in the queue waiting their turn.
Exactly. And this introduces variable delays, which network engineers call jitter.
And jitter is what destroys a real-time experience, right?
Yes, completely. If you are just downloading a large PDF document, a few milliseconds of jitter doesn't matter at all. The file still arrives and pieces itself together. But if you are speaking on a live video call, your voice is sliced into thousands of sequential packets.
So if they get delayed,
Right. If one packet of your voice takes 20 milliseconds to process through an intersection, but then the next packet takes 60 milliseconds because that specific router was suddenly busy processing some massive email attachment from someone else, your voice packets actually arrive at the destination out of order.
oh wow. So the receiving software on your laptop literally has to pause the video, wait for the delayed packets to arrive, and line them back up in the correct sequence before it can play the audio through your speakers.
Yep. And that waiting period, that is the robotic, staggered glitching you experience.
That makes so much sense. So the problem isn't the speed of the optical transport layer at all. The muscle is incredibly strong, but it's waiting on microscopic manual instructions at every single intersection.
Exactly.
Yeah.
Which highlights a really critical architectural flaw. If the network has virtually infinite brawn in the fiber optics, it desperately needs a faster, more centralized brain to manage the traffic.
And that brings us to the control and orchestration layer.
The network brain.
Right. This is where the source material introduces what is arguably the most profound shift in the history of internet infrastructure. Software-defined everything, or SDX.
It is a total game changer. For decades, the brain and the muscle were physically fused together inside every single piece of equipment.
Like the routers we were just talking about.
Exactly. Every single hardware router sitting in a server rack had its own internal brain, and it was making isolated decisions based only on what it could see directly in front of it. Software-defined networking fundamentally breaks that paradigm. It enforces an absolute separation of the control plane and the data plane.
Okay, with the control plane being the decision-making brain and the beta plane being the muscle actually moving the packets.
You got it.
So let's upgrade that traffic cop analogy from earlier. In the legacy telecom world, you literally needed a physical police officer standing at every single street corner in a major city, blowing a whistle and deciding which cars could go and when.
Right, that's your traditional hardware router.
Yeah.
The cop only knows about the cars at their specific intersection.
But in a software-defined network, you essentially pull all those local cops off the street, and instead you deploy an omniscient cloud-based software system that looks down at the entire city grid from above.
And that omniscient view changes everything. That central software brain is called the SDN controller. It has a holistic, real-time map of every single link in the network.
So it can see traffic jams before they happen.
Exactly. If that central controller sees that a primary fiber route between two cities is starting to get congested, it doesn't wait for the local intersections to get overwhelmed and start dropping packets.
It just fixes it.
Instantly.
Yeah.
It pushes a software policy down to the data plane and the edge devices, telling them to reroute all highly sensitive voice and video traffic over a secondary, clearer path, and it leaves the heavy, less urgent background data on the primary link. The muscle no longer thinks. It just follows centralized orders at the speed of light.
That is incredible. And separating the brain from the muscle leads to another massive technological leap. Legarski covers network functions virtualization, or NFV.
Yes, NFV.
Because once you extract the decision-making logic and put it into software, you realize you don't actually need highly specialized proprietary hardware boxes anymore.
Not at all. Historically, building a core network required these incredibly rigid physical appliances. If a telecom company needed to add a security firewall, or a load balancer, or an encryption engine to their facility, they had to go purchase a dedicated physical box from a major vendor.
And these boxes relied on ASICs, right? Application-specific integrated circuits.
Yep. These are custom microchips hardwired at the silicon level to solve one highly specific mathematical problem, like encryption incredibly fast.
But because they are hardwired at the silicon level, they are completely inflexible. You can't reprogram an encryption chip to suddenly act as a load balancer.
Exactly. So if you needed more capacity, you had to physically dispatch a technician in a truck to unbox a new piece of hardware, bolt it into a server rack, and manually wire it into the system.
Which takes forever. But network functions virtualization takes those specialized hardware tasks and turns them into software applications, like virtual machines or containers.
Right. And instead of running on those rigid ASICs, they run on standard commercial off-the-shelf servers.
COT servers.
Exactly. These COT servers are essentially just racks of generic, high-powered CPU cores, identical to the servers running cloud platforms worldwide.
So the implications for scalability are just massive. If a network provider suddenly experiences a surge in traffic in a specific region and needs more firewall capacity, they don't roll a truck to install a physical box.
No truck rolls needed.
They just log into an orchestration dashboard and spin up a new virtual firewall application on their existing generic servers in a matter of seconds. The network just becomes entirely fluid and elastic.
It really does. This virtualization revolution transformed enterprise data centers over a decade ago, but it has finally reached the deep core of telecommunications. But shifting the intelligence to software and relying on generic hardware completely upends the traditional business models of the industry.
Oh, absolutely. Which brings us to the final and perhaps most disruptive section of Legarski's breakdown mapping the stakeholder matrix.
That's the business side of it.
Right, because if the brain is now just software hosted in the cloud, and the muscle is just generic hardware you can buy from literally anyone, the old telecom monopolies that used to own the vertical stack from end to end have totally lost their physical moat.
They really have. The vertical silos have been completely dismantled.
So who actually runs this layered ecosystem today? Because the hierarchy has flattened into this interdependent matrix of entirely different players.
Yeah, let's look at the new players.
Yeah.
First, you have the traditional communication service providers, or CSPs,
Yeah.
the legacy household names. They recognize that if they only provide the raw optical transport pipes and the access layer connectivity, they will be marginalized.
Because selling pure bandwidth is just a race to the bottom.
Exactly. To survive, they are desperately trying to transform into techos, focusing on selling the software-defined platforms, cybersecurity, and cloud orchestration services that sit on top of their physical pipes.
Then you have the hyperscalers, the massive cloud computing giants like AWS and Azure.
Right. And Legarski details how they are aggressively moving into this space, basically acting as the edge cloud brains. They're physically installing their software platforms and cloud servers directly inside the traditional telecom providers' local switching facilities.
Wait, so by putting the omniscient software brain physically closer to the end user, they dramatically reduce the latency of those routing decisions.
Exactly. It's all about speed. Meanwhile, you have the physical real estate, so the actual steel towers reaching into the sky, and the underground trenches holding the fiber optic cables. Those are increasingly owned by neutral infrastructure providers known as towercos and fibercos.
And their entire business model is based on maximizing asset utilization.
Yes. Instead of two competing telecom carriers building two completely separate cell towers right next to each other, a neutral towerco builds a single tower and leases antenna space to both competitors simultaneously.
Makes total sense. And we also have the regulators, right? Like the ITU and 3GPP setting the interoperability rules for all these players.
Right, because without strict rules, none of these different systems could talk to each other.
Which is key, because this complex matrix of shared assets and overlapping responsibilities is entirely dependent on a concept called open and disaggregated architectures.
Yes.
Specifically, an initiative rapidly changing the industry known as Open RAN, or Open Radio Access Network.
Open RAN is huge. It's basically the final frontier in dismantling the proprietary lock-in of legacy vendors. Historically, the radio portion of the network, meaning the physical cell tower antenna and the baseband processing unit sitting on the ground below it, was a closed proprietary loop.
Meaning you had to buy everything from one company.
Exactly. If a carrier bought an antenna from a specific vendor, they were contractually and technologically forced to buy the processing unit and the controlling software from that exact same vendor. The equipment spoke a proprietary language.
Which is the ultimate vendor lock-in. But Open RAN shatters that by standardizing the application programming interfaces, or APIs, between these components.
It introduces open interfaces that act as universal translators.
So now a carrier can literally bolt an antenna from a specialized radio startup onto a tower, run a fiber line down to a generic commercial off-the-shelf server made by a completely different hardware manufacturer, and operate the entire site using cloud-based software written by a third independent software vendor.
It's totally mix and match.
I am fascinated by the modularity of this, but honestly, looking at it from a systemic level, I have to raise a massive red flag here for you listening.
Uh-oh, what's the red flag?
Well, think about what we were describing here. Your personal data enters through an antenna made by one vendor, sitting on a tower owned by a real estate company. It travels down into a generic server made by a second vendor, running software from a third vendor. It gets transported over a neutral company's optical glass and gets routed by an omniscient brain hosted on a hyperscaler's cloud platform.
Right.
Doesn't having this many interconnected components from this many different companies create a massive attack surface or a catastrophic point of failure? Like, if something breaks in that chain, who is even responsible for fixing it?
It is a very valid concern.
Yeah,
And frankly, it is the exact argument heavily promoted by legacy vendors who desperately want to maintain their closed ecosystems.
I'm sure they do.
But from a modern architectural standpoint, this extreme modularity is actually a profound defense mechanism. Disaggregation creates resilience.
Wait, how does fragmenting a system across half a dozen vendors make it more resilient?
Because it operates like interchangeable Lego bricks. Consider a legacy monolithic system where the antenna, processor, and software are completely fused. If that specific vendor software is found to have a critical zero-day security vulnerability, or if that vendor is suddenly deemed a national security risk due to geopolitical trade disputes, you are trapped.
Oh, I see.
Yeah, securing the network requires physically ripping out that vendor's equipment across thousands of cell sites. You have to replace the antennas, the baseband units, everything. It requires years of labor and billions of dollars in capital expenditure.
Because you can't surgically remove just the compromised part.
Precisely. The blast radius of a failure or vulnerability encompasses the entire site. But in a disaggregated Open RAN architecture, the standardized open interfaces isolate that blast radius.
Ah, so it's contained.
Exactly. If the software running the radio is compromised, you don't touch the physical antenna or the server. You simply push a remote update, or you swap the compromised software out for a competing vendor's software.
Just swap the Lego brick.
Right. And if a specialized hardware component dies, you don't have to wait 6 months for a proprietary ASIC chip to navigate a global supply chain. You just drive to a distributor, buy another generic commercial server, plug it in, and download the virtual machine onto it.
Wow. So the modularity literally prevents you from being held hostage by a single point of failure in the supply chain or a single software vulnerability.
Yes. And furthermore, it completely democratizes innovation.
How so?
Well, imagine a brilliant team of engineers at a small startup develops a revolutionary AI algorithm for optimizing how radio waves bounce off buildings in a crowded city. In the past, that software was useless unless they could also manufacture millions of physical antennas and compete with multi-billion-dollar legacy giants.
Which they could never do.
Right. But in an Open RAN world, they just sell the software application and the carriers install it on their generic servers.
It separates the brilliant ideas from the heavy manufacturing. It allows the software layer to iterate at the speed of the cloud rather than the speed of laying concrete and steel. We have covered immense ground today exploring Legarski's functional layers of the connectivity stack. So let's bring it all together so you can really visualize this in your daily life. Tomorrow, when you are walking down the street on a video call, and you seamlessly transition from your local Wi-Fi to a sprawling 5G network, you aren't just making a phone call.
Not at all. You are activating an entire invisible ecosystem.
You are initiating a highly orchestrated chain of events spanning the globe in milliseconds. You can literally picture the stack in action. The intelligent, converged access layer evaluating your environment and dynamically grabbing the best signal, passing the baton without dropping a single frame of video.
The ultimate relay race.
Right. And then those DWDM optical arteries shooting your data across the continent using dozens of colors of light perfectly separated on a single microscopic strand of glass.
Moving terabits of data.
Exactly. And the software-defined brain hovering in the cloud, constantly analyzing global traffic and pushing policies down to generic commercial servers to route your packets around congestion. And all of it orchestrated by a complex matrix of tech companies, neutral infrastructure providers, and software developers sharing components like modular building blocks.
It is a remarkable feat of modern engineering, honestly.
It really is. You are now fully equipped to see the invisible digital infrastructure that surrounds you every single day.
But as we step back and look at the trajectory of this disaggregation, it actually leaves us with one final, pretty provocative question to consider.
Okay, let's hear it.
We've established that the fundamental trend of the modern stack is the total abstraction of intelligence from physical hardware. Physical pipes and towers are becoming cheap, generic commodities, while the software running in the cloud dictates all the real value.
The brain is everything.
Exactly. If that trajectory holds, and telecommunications is no longer a linear utility running over a copper wire, but essentially just a highly complex software application running on generic servers. What stops the massive hyperscalers from simply swallowing the entire connectivity stack?
Oh, wow.
Right, if Amazon, Microsoft, and Google already own the cloud brains, and the physical infrastructure is just leased from neutral third parties, will traditional telecommunications companies even exist as we know them in 10 years?
That is wild to think about. Who ultimately owns the future of human connection?
That is the multi-trillion-dollar question.
From a single copper wire you can hold in your hand to an invisible global software ecosystem fighting for dominance in the cloud. Thanks for taking this deep dive with us. We'll see you next time.